Welcome. Today we are going to take lecture number 19. In this lecture, we are going to discuss about constant on time control method. And I am going to first talk about single loop constant on time control, two loop constant on time control in discontinuous conduction mode, and adaptive on time control. So, constant on time control in lecture number, I think earlier in week 2, we learned about constant on time modulation. So, you already know about the basic concept of constant on time modulation, and today we also want to show, I want to show the MATLAB building block, how to build constant on time, and we identified there is a problem in constant on time control. So, we need to incorporate minimum of time. First, constant on time, if we take the gate signal, this is the gate signal Q. In this gate signal, that instead of duty ratio, we will take this on time. This is my on time, and this on time is constant, and the smaller time indicate this is the off time, which will be adjusted from the feedback loop. Okay. So, a building block, that means if we take two signal x1 and x2, here two signals are compared and the comparator output QC. Actually, the edge, positive edge of this QC is detected, and then this output goes to a monoshot timer, and the monoshot timer gives us the actual gate signal. Okay. So, it is a comparator. Now, it requires an edge detection circuit and monostable multivibrator. The simplest voltage based logic. So, here we are going to consider the output voltage and the reference voltage. So, the output voltage and reference voltage both are compared. This is our output voltage and this is our reference voltage. Both are compared, and the output of the comparator, which is QC, that actually goes to the constant on time modulator. How does it work? That means, if we take a single loop feedback control, this is a DC-DC converter, and you can take any DC-DC converter. So, in the example case study, we are going to take a buck converter, but you can take boost as well as other converter also. So, here we are taking the feedback loop. This is my feedback loop, and output voltage is directly compared with the reference voltage. This is my reference voltage, and the comparator output goes to constant on time modulator. Now, we discuss about the very simple basic constant on time modulator. Suppose this is a waveform. Here we are going to show the output voltage when it crosses, that means it tries to go below the reference voltage. That means, if the output voltage goes below reference voltage, then we can find a positive edge of this. That means, it goes high, and this edge detection detect a positive edge here. That means, there will be a positive edge when there is when the output voltage try to go below the reference voltage. Then this trigger the monoshot timer, and the monoshot timer is loaded with a constant on time, that means a fixed value, and this is my constant on time. So, this is the duration of the on time when the switch is on, and this value is loaded in the constant on timer. So, I will show you the MATLAB implementation of this logic. Once the on time is elapsed, that means the timer finishes counting, then switch turns off, this Q goes low, and then output voltage again try to decrease. Again when it crosses Vref, then switch turns off. Okay. But in this method, let us consider a scenario where the converter undergoes a load step up transient, that means the load current has increased. So, let us say at this point there is a change in load step, that means it undergoes a load step transient of delta I0. Earlier it was I0, now it is I0 plus delta I0, that is the load current. So, first thing, what happens if V0 is less than Vref? That means, we know the logic, when output voltage crosses, that means this is the direction of output voltage, it crosses Vref, the monoshot timer detect, that means the edge detection circuit detects a positive edge, this is the edge detection circuit output, and this turn on, this enable this monoshot timer, and the monoshot timer goes high for the duration which is set by constant on time, and then it turns off. When it turns off, then because there is a load step up transient, in general in under steady state it is supposed to increase the output voltage. That means the output voltage was supposed to increase and it should go above Vref. That was our traditional waveform under steady state. But because of the load transient, step up transient, the capacitor current is negative for a certain duration when the output cannot increase. So, it will decrease. So, that means in this time V dash, the output voltage is lower than Vref. So, the output of the comparator is high, continue to remain high at high, and we cannot get any positive edge here. Then what will happen? Then we cannot turn on the timer again. That means the timer cannot turn on. As a result, no on time. That means the switch remains off. That means if V dash is less than Vref, this is my V dash, okay, at t equal to t dash, then what will happen? The QC continue to remain high and no rising is detected, and this cannot enable the timer. This monoshot timer cannot be enabled. As a result, the Q gate signals remains low, or it is turned off. It continue to remain turned off, and then the output voltage will further decrease and ultimately voltage will collapse. So, this process of simple constant on time implementation cannot be used in general circuit because it will lead to the collapse of the output voltage, particularly during load step up transient. So, that is why in most of the commercial product, in order to solve this problem, what we have to do? We have to introduce a minimum off time. After that, we need to check the status. If after a certain, that means once the switch is turned off, it will wait for certain time and check whether the comparator output is still remain high or not. If it is high, that means output voltage is smaller than reference voltage, then we have to provide another trigger pulse to turn on this monoshot timer. Okay? That means, how does it work? So, that means this part is the minimum off time that should be introduced, and that we have discussed in the very previous class in week 2. How does it work? So, we should check the status of the gate signal. Okay? That means when the switch was on, that means the monoshot timer was high, then at some point when the timer finishes its timing value or the counting value, then the switch turns off, and that time you detect a falling edge of the switching signal. This falling edge is delayed by a time tau d, and this delay can be realized using a shift register. So, this is a delayed edge detection signal which detect a negative edge of the switching gate signal, and that is delayed by tau d, and this delay time is nothing but, this tau d is nothing but our minimum of time, minimum of time we will discuss. Okay? So, then it checks with the output of the comparator. As I said, after this delay time, if the comparator output is high, that means our V0 is less than Vref, it indicate we need to turn on the switch because output voltage is going down. So, this is high, then this output will goes high, this will go high at this time, and then it is also ANDed with the actual trigger signal. So, that if either of them is high, this will go high. If any edge is detected, either the edge of the rising edge or the delayed falling edge, is any of these edge is detected high edge, this edge is now used for the monoshot timer. That means earlier we are using, this was our earlier trigger pulse, but now it is modified by introducing a minimum of time. Okay? So, that means the turn on problem in constant on time, we need to identify the falling edge of the gate signal, then we need to delay, and then we need to AND with the output of the comparator, and this will actually OR, the output of the AND gate is ORed with the original rising edge of the trigger pulse, and then the resultant output of the OR gate, that is the resultant trigger pulse, is used to trigger the monoshot timer. Okay. So, inside a that means monoshot timer, we have a shift register, and this is what we have discussed: positive edge detection, negative edge detection, a time delay, a gate signal is required, a minimum off time to be set, and the constant on time to be loaded. So, how to realize in MATLAB? In MATLAB, this can be realized by this comparator. You can see this comparator is nothing but this comparator. Okay. And MATLAB, you will get the greater than, less than, the equality sign. Here, if Vref is greater than V0, that logic is implemented here. This is the reference voltage, this is the output voltage in the MATLAB. So, first edge detection circuit, this circuit is realized here, and the minimum off time generation is the whole circuit here. So, this is the minimum off time generation circuit, this is here. And what is the input to the minimum off time? The one input you can see is the output of the comparator, that is the QC. That means this is my QC. The other input is the gate pulse, which is Q, that means this is also Q. The other input is Q, and for the OR input we are using the FTR, that is the rising edge detection circuit, the output of the positive like rising edge detection circuit, and this is ORed, and this is actually the original monoshot timer. That means if I take about this one, so this is this block, and in MATLAB you can get this monostable, where the on time will be set according to the on time constant on time value. And if we go inside this block, what is this? That means this is an analogous circuit in the schematic, and this is a MATLAB implementation. Now, what is there inside this block? So, this block, I am talking about this particular block. If you take this block, again it takes Q and QC as the input, and QC directly ANDed, that we know, and there is a negative edge detection circuit, which is nothing but this one. That means if we take this one, this is our negative edge detection circuit, and this delayed time is realized by these two block in the MATLAB. This is my delayed signal is realized. Okay. And then this is the AND gate, and the overall thing is ORed here. That means this is our OR signal, and this is our OR signal. Okay. So, with this we can implement the MATLAB, and I will show you how to realize in MATLAB. Now, that means if we go back to the MATLAB, let us go back to the MATLAB. I want to show you the implementation of constant on time. Okay. So, this converter block we already discussed. That means this converter we have already discussed, and this same enable everything we have discussed, the input voltage, how to make this model, and this is your load resistance, resistive load. We can use any other load also. Let us take it little bit this side. Okay. This is a resistive load, and then this is a constant on time control. If you go inside, which we have discussed now. Okay. So, here what are you doing? Two reference signals and output voltage, they are compared. This is the first positive edge detection circuit, and this whole block actually implement the delay time, that is the minimum off time. Then this is the actual monostable multivibrator. If you go, the constant on time you can set it from here, and this is a gate pulse. Okay. So, we can check this simulation by using this constant on time in the simulation model. So, we can use a DCM enabled to be 1 under discontinuous conduction mode. We can use 100 milliampere current, and let us see how does it work. So, you can see this is a constant on time where the switching frequency will vary. That means, this is the duration of the on time which we set, and we can decide based on our requirement. But interestingly, you will find how does it work this logic. If you zoom this one of the cycle, output voltage cycle. So, initially whenever the output voltage, so if we check that whenever the output voltage try to cross this particular reference voltage which is 1 volt, then switch turns on and that turns on for a certain on time duration, and then okay, if I take let us say this is my duration, let us say if we take around 0.5, okay, one cycle we can take. So, around 0.5 let us take. Okay. So, we will take from 0.505 to 50 here, and we take here 505 to 5053. Okay. So, you see whenever the output voltage actually try to cross this reference voltage here, then switch turns on for a fixed on time duration. Then whenever the on time is elapsed, the switch turns off, it hit the 0 current discontinuous conduction mode, and output voltage actually slowly decreases because the load current is very low. Whenever again it hit, then again turns on. So, this process, the constant on time logic work in this process. That means, now we understood that how does it work. The next part is that okay. So, now we have implemented the single loop voltage mode control, where this output voltage here, the output voltage is compared with the reference voltage, and then the comparator output goes to the modulator, and then modulator will generate the gate signal, and that turn on and turn off the DC-DC converter. Now, we want to simulate, like we have already implemented this for constant on time control. We want to simulate for different input voltage. That means, our reference voltage is 1 volt, input voltage is 15 volt, and then input voltage again is 8 volt, and our load resistance is 0.1, that means 100 0.1 ohm. This is for continuous conduction mode. Okay. Then we will also run the steady state condition at different load current, then we will do transient simulation. Okay. Let us first go to the MATLAB and check. Okay. So, what are you going to discuss? The first condition we will take, where input voltage is 15 volt and 8 volt for R equal to 0.1. Okay, let us go there. So, if I take R equal to 0.1, that means let us take directly R equal to 0.1. So, I have already explained this MATLAB implementation. So, I am not going to repeat this, and this controller in this case does not make any sense because we have not provided any controller here. You can see if you go inside, there is no controller here, it is just a simple input and output comparison. Then, so R equal to 0.1 ohm. So, initially we want to run for one condition, which is V in equal to 15 volt. That means, here we will set V in equal to 15 volt. Let us run it. So, we want to show this is for V in equal to 15 volt, and we want to overlap this waveform for V in equal to 8 volt. Okay. Now, we are talking about V in equal to 8 volt, and we want to repeat the simulation with the same load condition and check what happens. Okay. Now, here so here what can we find? First of all, if we take the inductor current around this time period, let us say we are talking about from 0.5 millisecond to 0.51, 0.5 to 0.505 here. So, that means in red color we have decreased the input voltage, which initially for the blue corresponds to the input voltage of, just a minute. So, here we are talking about 0.5 to 0.506, okay, 0.506. Okay. So, this red color, blue one corresponds to 15 volt and the red one corresponds to 8 volt. So, what happened here? And in both the cases the logic, it looks like whenever the reference voltage, the output voltage touches this Vref, which is 1 volt, then switch turns on, and switch turns on for the given on time. So, in both cases the on times are same, but since the first case blue one, the input voltage is higher, that means for the same on time the current ripple will be larger because the slope is higher. You can see the slope is higher because the input voltage is higher. In the red one, the slope is smaller and the same input voltage, same on time, the ripple current will be smaller. So, as a result, the switching frequency are different for different input voltage condition. Okay? Alright. So, these two are the results for two different input voltage condition. Okay. Now, coming to the next simulation, we want another steady state condition where input voltage remains at 12 volt, which is originally set in the parameter set, but we want to change the load resistance from 0.1 to 10 ohm. Okay, let us see what happens. Okay, so we will change this. Now, we are going to consider two different load resistance. So, in one case the load resistance is 0.1, which is, let us say, in the red color, and in the other case we want to change it to 10 and we need to make it, let us say, blue color. Here the red color, red trace corresponds to, okay. All right. Okay. So, what we will find here? Okay. We will zoom it. That means under continuous conduction mode, okay, let us run it in CCM because we have enabled DCM. Let us continue in CCM. Okay. So, blue trace corresponds to, okay, this is 1 and the other one we want to do 0.1 and that corresponds to red trace. Okay. Okay. All right. So, here what do we want to do? Okay. If I take few cycle around 0.5 to 0.51, 0.5 to 0.51. Okay, so if we take 0.5 to 0.51, what we will find that the time periods are more or less same. There is a time shift you can see, but the switching period, if you take, what is the switching period? For this case, it is close to 2 because 0.502 to 0.504. So, 0.002 millisecond, that means 2 microsecond. In this case, it is slightly higher than, or it is almost, again if you take this cycle to this cycle, it is again almost 2 microsecond. So, that means there we are getting the switching frequency close to our desired 2 microsecond because it corresponds to 500 kilohertz, but there is a time shift because both are variable frequency operation. So, any perturbation that will shift the time also. That means, we can nearly achieve the fixed switching frequency or desired switching frequency for, because we set the on time based on V0 Vref by Vin. Okay. alright. So, nearly constant, I will not say exactly constant, but nearly constant. Okay. So, now coming to our, that means two things we have. Now, we want to do transient simulation. What happen if Vin is equal to, so this part we are going to consider in another lecture where we will make a comparative transient performance. So, for the time being, let us just make a transient simulation R equal to change in Vin and change in Vref. Let us do the transient simulation. Now, first, what are we going to do? We want to make a load transient. So, let us keep this is for 1 ohm. What is the value of the resistance? So, we will set R changes from 10 to 0.05 and Vref is equal to 1 volt. So, R changes from 10 ohm to 0.05. Okay. That means, let us go for, we will take R1, we will take R1. R1 equal to how much, from what to where? It goes from 0.1 to, sorry, 10 ohm to 0.05. Okay. 10 ohm and R2 equal to 0.05. And how can we make load transient? Okay, let us go. There are multiple way of doing transient, but in this case we are going to take this way. So, we will introduce a switch, that means we already have some switch. So, we will take one of the switch, okay, and we will introduce a switch here. Okay. So, this switch is my load resistance and let us go to this switch. So, this is my load resistance. So, initially it will take R1, that means there are two load, one is R1 and the other one I want to take R2. Let us say this is my R2, because it should change R2. Okay. That means, let us connect to this for load transient and this should be connected to the output voltage and we need to provide a transient like sources. Yeah. So, we need to apply a step command, that means when do you want the transient. This is will be 1. So, at what time? It is initially 0, it becomes high, and what is the step time? At what time we are going to change? Let us say at 0.5 millisecond we are going to see the transient. Okay. Now, let us run this simulation. Okay. So, we are running for 1 millisecond. Let us try. Yes. So, this is the load transient performance. You can see initially we actually, I think it changes from R2 to R1. So, let us, okay, yeah, it changes from, so we have to take this as R2 and this one as the R1. Okay. Yes. So, this is a step of load transient. How does it work? So, you can see initially when at this point we are applying a step up transient, that means we are changing the load. Initially the load resistance were set to 10 ohm, that means, and it is in continuous conduction mode throughout, and this time we have turned on, we have enabled that, you know, there is a load transient, and during this time, since there is a minimum off time, you can see the minimum off time, this is a constant on time control. That is why after certain duration it is getting turned off and that is slowing down the process. Okay. So, we can improve this transient performance by changing. So, we will retain the same value and let us run. We want to, what will happen, because here we set the minimum, I mean, as I said, here we have to set a minimum off time. if I change this to very small, so minimum of time I choose t by 20. That means if t equal to 2 microsecond, so you are taking 200 nanosecond is my minimum of time. But if I now reduces to 20 nanosecond, then we want to see what happened. So we want to repeat this simulation and check what happened in the load transient response. So it will overlap, the two response will overlap. Okay, so some improvement we can see in the transient performance if we can reduce the off time, but the transient response seems to be fast, but there is a significant overshoot and that we have to take care. Okay, so this is the transient performance that we have checked. Similarly, we can make the supply transient. That means how to make supply transient? So we will keep load equal to 0.1 ohm and we will change V in from 12 to 8 volt. How to do that? We can do that. So if we again go there, now we will take directly from this R1, okay, or maybe we can take R2. What is my R2? So we will take this gate signal far away. Okay, so we will, for the time being, let us, okay. Now what are we going to do? We want to incorporate one summing block, which is summing block, and here we want to make a load supply transient. How to make it? That means initially I will take this 12 volt is the input. Now here at 0.5 I will make minus, let us say 4 volt. That means supply changes from initially it was 12 volt and now we are subtracting by 4, so it will be 8, 12 to 8. Okay, and R2 how much we are taking? R2 we are taking R2 0.01, let us say 0.1. Let us run. Now we are making a supply transient and see what happens. So if you make a supply transient, you will find the transient performance is really fast, but there is a change in switching frequency and also there is a change in output voltage ripple. So this, and we will see this is a drawback of the constant on time control. If we keep the on time constant, the voltage ripple can get significantly affected when there is a change in input voltage. But in case of change in load resistance, it was not a problem. In continuous conduction mode, it will closely maintain the switching frequency, but it is not the case for the input voltage variation. Okay. So let us go. That means we have discussed about the steady state condition, we have discussed about transient condition for this constant on time control. Now another feedback control using constant on time modulator is called V square control, in which V square control, two loop control, there is one loop which directly takes the output voltage and the other loop it is the error voltage with compensator. So this loop is the inner loop which takes the first dynamics of the voltage ripple, and this loop is slower outer loop. So this is also known as V square control. Now single loop current control, we talked about single loop voltage control, we can also talk about single loop current control. Here the inductor current is directly compared with the reference current and then it goes to that constant on time modulator and we can control the current directly. It can be used for battery charging, for constant current mode, and it is very much used for boost converter in terms of critical conduction mode in PFC, like unity, for power factor correction, like a boost converter. And if you use critical conduction mode, the constant on time modulator can perfectly track the current and you can achieve closely unity power factor, okay, but with a variable switching frequency. Similarly, constant current loop can be used for battery charging application, where if you take a boost converter or a buck converter, the reference current, constant on time, we control the valley current, it is known as valley current, and we will compare this result. And the ripple current for buck converter, we know that V in minus V0 by L, and if we set for a given input output voltage, if we can set the right, if we can identify the right value of ripple current, or we can accordingly adjust the on time to get a desired current ripple, then we can control the reference current by battery charger by setting a suitable delta IL by selecting the on time correctly, and we can track this. This is possible. In case of constant on time current mode control, okay, current mode on time control. So, let us go back and two loop control. How does it look like in simulation? Okay. So, if we go back to our MATLAB file, now I want to first, so that means we have run for this model constant on time control, we have simulated and we have also shown the waveform. Now, we are talking about constant on time current mode control is also possible. That means, if you go to constant on time control, yeah, here we can replace the current loop control by voltage, voltage, this is totally voltage based control, we can replace with a current based control also, okay, that is possible, okay, and we will compare this result in a different session where we will compare the performance of different control scheme. In discontinuous conduction mode, we have shown that constant on time control is frequently used in commercial product. Why? Because we have seen the diagram, that means in constant on time control we saw if we fix the on time, if we keep the on time fixed, then the time period will vary based on the load current condition, based on the rate of discharge of the output voltage. This is the slope, this is the discharge slope, and how does it vary? Because during zero inductor current, this will be purely dependent on the amount of load current. That means, higher the load current, the rate of discharge will be faster, smaller the load current, it will be slower. So, accordingly the time period will be adjusted. And if you do DC steady state analysis in discontinuous conduction mode, and if you keep on deriving using the capacitor charge balance, that means different charges shown here, and by calculating the capacitor charge balance, it can be shown that the switching frequency, the effective time period, or effective switching frequency under constant on time control, this is the derivation. For a given input voltage output voltage, this quantity is constant, if we do not change input output voltage. This quantity is also constant if we keep the on time constant, which indicate the switching frequency is directly proportional to load current. That means, the switching frequency is directly proportional to load current, because under given input output voltage condition, this is constant, this is also constant. And this is very powerful for light load efficiency improvement, and we have a session dedicated to this, and I will discuss more about this discontinuous conduction mode, but this is today I am just going to touch upon how the output voltage ripple changes. Now, so we identified the switching frequency under discontinuous conduction mode is proportional to load current under constant on time control. What will happen if what will happen with their output voltage? That means, if the load current changes and if we keep on time constant, how is it going to affect the output voltage? So, if we take the output voltage and under our light load condition, the current ripple may be much higher than the average inductor current, and if we put this assumption, then it can be shown that the output voltage ripple can be approximated by this expression, which means if we keep this quantity constant, that means for a given input voltage output voltage, given inductor and capacitor, and given on time, the output voltage becomes more or less constant. That means, for load current changes, the output voltage is not going to get affected significantly, very small, okay. But that means, let us take a simulation, let us go to our MATLAB model and check our simulation case study. Okay. So, we are talking about constant we are talking about the light load condition, 2 load resistance. So, this is where we are taking from, let us say R1. Now, what are we going to do? So, here we want to run in discontinuous conduction mode. So, we want to make DCM enabled to be 1 and load resistance let us take okay. So, we will take, instead of a load resistance, let us take 2 conditions. One is 100 milliampere current, okay, and let us run it, and it is used for blue color stress. And now, so here we are making input voltage changes. So, let us do not change it, we are not changing any input voltage transient. So, I want to show you for 12 volt input, this is the steady state condition. Now, we want to go to 10 milliampere current and we want to use a rate stress and show what is the, we want to see how does it change. Okay. Now, okay. So, you see the red and blue. So, red is a 10 milliampere and blue is the 100 milliampere. So, in between you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, that means as I said, the switching frequency is proportional to load current. That means if the load current is decreased by 10 times, the switching frequency is decreased by 10 times and the time period is increased by 10 times, and this exactly happened because you see in between 2 red waveform, periodic waveform, there are 10 such blue color waveforms. So, that means the 10 time fast higher switching frequency for higher load current, for light load current it is. So, it is a, we can prove that this actually changes the load current is switching frequency is proportional to load current, this is proved. Another interesting fact that we have just now we have seen, the output voltage ripple is almost remain constant. Output voltage ripple for both the cases, if you take the output voltage ripple, they are more or less remain constant. That means, under constant on time control for varying load current in DCM, the voltage ripple does not get affected, I mean significantly affected, very minor changes. So, this is a very good technique, that means it retain the, and we can select the on time to keep it within the band. Okay. But it also has a problem when there is a change in input voltage, because you see this expression shows when there is a change in input voltage and both the terms are in the numerator. So, it can drastically increase the output voltage ripple and it can deviate for higher input voltage, can deviate the voltage tolerable limit. So, we need to do something adaptation in the on time. Okay. The same thing can be proved in boost converter, and if you draw the capacitor current waveform, and that you can check by yourself. That means, all the Q1, Q2, Q3, Q4 can be derived from this capacitor charge balance, and using the charge balance principle you will arrive the same expression what we derive here also. FSW is proportional to I0 for given input output voltage and given on time under constant on time control. Okay. And for boost converter also, if you see the load current output voltage ripple, it is the same principle of the buck converter, only when input output voltage remain constant, the voltage ripple will be almost insensitive to load current variation. Okay. And the adaptive on time. So, that means what will happen if there is a change in input voltage. Okay. Now, we are talking about 2 input voltage condition. Let us first stop this. Now, in one case, let us say it is under 100 milliampere, okay, and this case we are talking the input voltage is 12 volt, it is already 12 volt. So, there is no problem, the blue car. Now, we want to make a changes input voltage to 8 volt, okay, or maybe initially let us take 8 volt, 8 volt is our input. Now, we are making input voltage 12 volt and we are using a rate trace for 12 volt and run it. What we will find that in 12 volt input not only the time period has changed, but it has significantly increased the output voltage ripple and it can go beyond the tolerable limit. So, we need to do some sort of adaptation. So, this is called adaptive on time control. How do you do that? Instead of using a constant on time through a timer circuit, we can generate this on time by keeping a fixed current reference I peak. And if we do that, then this is our original expression, and what is the, if we keep peak current, then the on time can be calculated by peak current by the slope, and if you substitute for a buck converter, we will get that delta V0 is this, and if the input voltage, since we are talking about 12 volt input and 1 volt output, so our input is much higher than in output. So, then this expression will be almost insensitive to input voltage change. That means, we will discuss in the context of light load control. So, if we keep a current based constant on time or PFM control, it is also known as adaptive on time, or it is also known as PFM, pulse frequency PFM control, where the output voltage ripple, because under fixed input voltage the on time remains same, because this expression none of these quantities are changing. So, then it retain the linear variation with the load current, that property is retained. Under variation in input voltage, it retains the ripple information, that means ripple constant. So, this is used in many commercial products, and we will discuss about other adaptation method. So, that means voltage and current based single loop constant on time controls are discussed, 2 loop constant on time control, which is a valley current mode control was discussed, constant on time control in discontinuous conduction mode and its advantages in light load are discussed, and the current based adaptive on time PFM technique was also discussed. So, with this we are going to finish here. Thank you very much.